Hi, thank you. So as John said, I'm right now moving from ETH to NYU. For the past 2.5 years, I've been mostly doing pure mathematics. Before that, I was doing stuff that was closer to machine learning. And over the past couple of months, I've started again. I really wanted to talk about the really new stuff, but last minute, I realized that maybe it wasn't that so right. So I'm going to talk about stuff that's a bit older, like 2 years old, but I think is still quite relevant, which is this question about how do we sample random variables in the simplest case. So luckily for me, the main problem, the main setup has been prevalent over the last day and a half in multiple talks. I have a very high dimensional distribution, potentially, with a nice density, where the concept of nice is very unknown. And I want to generate samples from this random variable. More importantly, I don't really know how this random variable is made. There's no like secret algorithm I'm trying to learn or something like that. So I need to design some sort of general purpose algorithm that gets a density that's promised to be nice and is able to return random variables that come more or less from with this law. So good news and bad news, there's a lot of ways of doing this. If you're very, very naive, historically, there's algorithms like rejection sampling, which work terribly in high dimensions. There's diffusion type algorithms or Markov chain type algorithms, which sort of try to iteratively improve on a solution until you get to a nice one. Or, you could try to just straight up generate your random variable as a push forward of a known random variable in a single step. There's many ways. There's as many algorithms as people implementing algorithms, probably a lot more. And, we sort of the goal for today is to find the best one. So first question, before we even talk about what is the best algorithm, there's a lot of ways to describe a random variable. First one would be, I give you a very long list of samples. This is the situation, for example, in machine learning, like diffusion models, where I give you a lot of pictures of bedrooms, as we saw before, and now you want to generate new pictures of bedrooms. Another situation is you've already somehow, out of that, learned a density, some sort of maybe a normalized probability density over the space of bedrooms, and now you want to generate one. It's probably not going to be convex, so probably like traditional like Markov chain algorithms are not going to work, and so on. And the last one, which is very important, very useful in physics, is when the distribution is not completely random. It has like some law to it, but you still want to generate samples from this random variable. Okay, so to the task of finding the best algorithms. So first, I even have to define what is best. So for me, best is going to be algorithms that try to minimize the access to the density. I will assume that the density is well known, that there's no errors in the density, and you have an algorithm that's able to query it. Maybe this density comes from a neural network. Maybe it comes from a complicated piece of software. So you don't want to have to call it a lot of times. I assume that the algorithms that we're going to build are going to be relatively simple. Therefore, most of the cost is going to be in evaluating the density or its gradient. And that's what we're trying to minimize. Now, what we know is that if you consider like arbitrary densities in RD, this problem is effectively impossible. Just consider a situation where I'm like in 1,000 dimensions and I hide a density that has a lot of like bumps all over the place. Any algorithm will have to find these bumps. So basically, you have to explore the whole space before even being able to say anything about the distribution. Maybe you missed 99% of the mass, which is in a bump in a corner. It's a completely hopeless problem. So getting inspiration from convex analysis, I'm going to define log concave distributions. Log concave distributions are the morally distributions that have a single bump. Mathematically, they're distributions of the form e to the minus v, where v is convex. And in our case, we're going to assume that v has some sort of regularity. In other words, it's a function that's not too big, not like the Hessian is not too big, not too small. So you should think of them as Gaussian-ish. Maybe they're not exactly a Gaussian. They can be like, a little bit more square or something like that. But in spirit, they're sort of Gaussian distributions. They're, for example, the ones where these diffusion type algorithms could work. The reason being that I don't have local minima that I can get stuck on because I'm like a unimodal distribution. Now, again, the inspiration is convex optimization. If I run any of these like Langevin type algorithms, I'm going to be looking at the potential. The potential is convex. But not only that, we have a really beautiful theory at this point for convex optimization. First, we have the whole classical theory that tells me how good an algorithm can do, no matter what the algorithm is. We have universal bounds that tell me you're trying to optimize a convex function, don't think too hard. There's easy algorithms that are going to do it. But not only that, historically, the way that we found the best existing algorithms was by inspecting the lower bounds. Like people didn't fully realize which were the existing algorithms until they started to find lower bounds. They saw that, they didn't seem to be able to build something that's worse than what's known as Nesterov's worst function. And then, well, maybe if this one's the worst, I have to find an algorithm that works very well there. And Nesterov did that, found Nesterov's algorithm, we're very happy. So, in a dream world, we want to copy that. Before continuing, I wanted to do a little bit of a sanity check. Did we oversimplify? We started with these problems about finding samples from high-dimensional distributions. And now I'm telling you, let's look at something that basically looks like a Gaussian. My claim is that no, that these are, not my claim, the sort of well-understood claim is that this is a central question. On one hand, we care about convex optimization. This is literally the analog in sampling. Maybe just by analogy, we should care about it. Another one, which is great, is that even when we're solving non-convex problems, we like to do two things. The first one is just pretend they're convex. And the other one, if we don't want to pretend and we want to be rigorous, is we convexify them. So let's say, for example, that you want to learn a function. Oh, there's an extra x. This x should not be here. Let's say you want to minimize the function phi of x. And the function phi of x is non-convex, and you don't know how to do that. One algorithm that you could run is you minimize, how do you call it? Instead of minimizing straight up the function, you minimize the function plus a quadratic term. This has as many names as different fields use this: implicit Euler, JKO, minimizing movements. This is a universal feature. I'm trying to minimize a very complicated problem. I optimize step by step by adding a parabolic regularizer that guarantees to me that the problem is convex. In sampling, you see the same. So we've had these processes that we've seen these days, these diffusion processes, which we've looked at as continuous time processes. You could also discretize these processes that interpolate from the distribution of bedrooms to a Gaussian distribution. And instead of trying to do the continuous flow, when you're doing it in a computer, you will have to go from one step to from t equals to 0.1, 0.2, and so on. The conditional distribution that you will have when you move from one step to the next is going to be strongly log concave. It's going to be dominated by the Gaussian part of the drift, which is going to be a tiny drift, or a very concentrated Gaussian that's going to make you essentially log concave. So these type of questions of sampling from strongly log concave random variables show up as the intermediate short time step when you're running discrete time and you want to understand discrete time diffusion processes. So, okay, we have a problem. It seems set up. It seems doable. And most importantly, it also seems useful. Now, let's actually formalize what we want to do. So I'm going to give you a distribution, which is going to be of the form e to the minus v. V is convex. I like convex functions. So I'm just going to focus on v from now on. And I'm going to promise you that the Hessian's not too bad. And now what I want is to produce a sample from this distribution. I want the sample not to be perfect, but not to be too bad. So, and I'm going to get access to v and to the gradient. Basically the same situation as optimization and what happens in real case scenarios. Now, the question is, what's the best algorithm in the sense of how many queries does the best algorithm take? To clarify a little bit more the setup, in this talk, I'm going to fix the quality parameter. For real-world applications, 0.1% agreement is 99.9% agreement is more than enough. I don't have to see the asymptotics. I will assume that I want to produce only one sample. It does happen sometimes that producing 1 million samples is not much more expensive than producing one, because in the process of producing one, you've learned so much information that you may as well reuse it. And the last one that I'm going to assume is that you already know, maybe not exactly, we could even pretend roughly, that you roughly know where the mode of the distribution is. If you start your optimization extremely far from the mode of the distribution, you're just going to spend most of the time trying to find the mode. So, and then you just have to add how much time it's going to take you to find the region where the mass is, plus the time to do something interesting where the mass is. One of them is an optimization problem. Optimization we understand. The other one is the sampling problem, which is the interesting one for us today. So I'm going to assume that we are in the sampling situation. What are the sort of well-known algorithms? One is this thing called Underdan-Langevin with randomized midpoint. Basically, what this is you devise some complicated stochastic differential equation, which is a little bit more advanced than just like the one we've seen these days, which sort of simulates a Hamiltonian dynamical system on top of your potential plus some extra noise. And this explores the space fast, and you also are very careful in the way you sample the points and so on, and you can get these sort of dependencies for this algorithm. So we can show that this algorithm converges at least this fast. Another one would be, well, it's a blob. It's I have a bump. I can approximate my bump sort of by an ellipsoid. I can renormalize my distribution so that it's isotropic, and then sample from the isotropic distribution because it's already been isotropized. This works very well in low dimensions. High dimensions, well, it's very expensive. So depending on if you're in a very high dimensional regime or low dimensional regime, we have algorithms that work better. So you can see the one on the top is polynomial in kappa. The one on the bottom is logarithmic in kappa. So if I'm in low dimensions, I don't really care about kappa. Okay, so now let's say again in the same situation, I have this class of non-negative potentials. This is roughly what we're going to see today. So any algorithm that you come up with, and this is sort of like the punchline, we can find estimates that are independent of which algorithm you're going to use. So any algorithm that takes a certain amount of queries and produces something that's not too terrible, let's say with at most a 1% error, will require, in dimension 1, at least log kappa samples. So it's essentially free. In dimension 2 and higher, you always need at least log kappa queries. And if you go up, then you need something that's roughly polynomial in D or kappa. If either D or kappa are non-negligible, this is already big. So the question is, how does one prove statements that are independent of the algorithm? There have been plenty of results where you give me, how do you call it? You give me an algorithm, and then I'm going to construct a function that's going to fool your particular algorithm. So there's been this sort of arms race where someone will come up with an algorithm, someone will create a function that's particularly bad for that algorithm, someone will create a better algorithm that's not bad for that function, and so on. So what do we do when we just don't want to care about the algorithm? So I'm going to describe a little bit of a challenge setup. So the first thing that you're going to do is you're going to pick a family of test examples, a family of enemies that we're going to show are universally hard. There's essentially two types of log concave distributions that I understand, or two ways to think about them. First one, Gaussians. We like Gaussians, but they have a problem. A Gaussian is essentially represented by a matrix. A matrix has D by D entries. Every time I make a query, I can learn D of those entries. So, at most, no matter how badly conditioned it is, if I do D questions, I will learn the whole covariance matrix perfectly, and I will know the answer. So, it's going to work well, maybe in very high dimensions when kappa is very small. And then another thing that I could do is I could design some sort of bump functions that are very good at hiding themselves in space. Here, the bottleneck is human imagination. This is very easy to do in low dimensions. As you go up, it's harder. The good thing is that this is not going to be in dimension 2. Here, 2 samples are enough. Maybe there we can do something more smarter than 2 samples. The second thing that I'm going to need is a challenge, something that I want to learn. Typical challenges would be the variance. Maybe I want to learn the total variance of my distribution, the largest eigenvariance of the covariance. Or if you chose a finite family, maybe the challenge is learning exactly the element that you want. So I'm gonna define a challenge that we have to solve. And then what I'm gonna do is I am gonna bound in two different ways how hard it is to learn the challenge. First thing that I'm gonna do is I'm gonna show you that if you have access to samples, this is a very easy challenge. Let's say you want to learn the variance. Well, if I give you 1,000 samples, you just empirically compute the variance, and you're going to get it very well because you have 1,000 samples. And most of the work is going to be in showing that learning this challenge from queries is actually a very hard task. Now, once I'm done with those two, it's just a matter of accounting. So let's pretend that I could produce samples very efficient, that it was very efficient to produce samples. Then I could produce an algorithm that solves the challenge using queries in the following way. First, I use the queries, and I turn them into samples by paying however my algorithm costs. And then I use the very cheap algorithm that I have for samples. But I know that it's very hard to solve the problem from queries, which means that the conversion rate, the price that I have to pay to go from queries to samples, has to be very big, because otherwise I would be able to have some sort of illegal arbitrage behind this. So I have this inequality, and I'm going to use this inequality to bound n. Okay, distributions are hard. There is a very slight variation of the problem that's a lot easier. So let's for a second stop thinking about smooth, smooth log concave random variables. A Gaussian is a bump for me. A bump is a convex set. So instead of trying to learn random variables, I could try to learn convex sets. So I have a similar question right now. How does the size of a convex set relate to the size of an associated Gaussian? Well, if my Gaussian had width kappa, I will assume that my convex set has width kappa, but I also had my Gaussians couldn't be very narrow because the Hessian was bounded from above by k. So I'm going to be considering a family of convex sets that are contained in a very big ball of size k and contain a tiny ball of size 1 over k. And now I can ask the same question as before. Produce a sample from this distribution. Now it's a convex set. I don't have access to gradients. I only have access to one thing, which is the membership oracle. It tells me, am I inside of the convex set? Am I outside of the convex set? Now, the good thing is that now I get access to information theory. Information theory tells me that I'm only going to get one bit of information per query. And this, the spoiler is that this generalizes. I will later on build families of log concave measures where every time you measure, you also get one bit per query. So basically the punchline of all of this approach is that you can do all of your computations in the very easy world of convex sets where accounting for how much information I get and so on is absolutely trivial, and then bootstrap all of my knowledge that I got in the world of convex sets to log concave measures where a priori the situation is very confusing for free. So you want to produce a random sample from the convex set, but you don't know who the convex set is. So naively, you could do some sort of rejection sampling, where you sample a point. If it's not inside, you throw it away and you try again. But this will be very expensive. But maybe you could use the information smartly to sort of guess the set. I start sampling points before, some sort of sinking ships game. To try to find a point that's inside at the next step. So it's a much harder problem. Naively, it is a much harder problem than the log concave one, because on the log concave one, you would think you get a gradient direction that's helping you. The whole point is that it doesn't quite help you. It helps you with powers of kappa, but there's a log, and then all of these powers are going to wash out. So we have this problem, which is much easier. You give me a point, I tell you if it's inside or not. And at some point, you'll have to give me a uniform point. If you design a very advanced algorithm, it's not going to be uniform inside the point, because your points that you're picking may be conditional on everything you did before. So you have to be a bit more careful. But in practice, all of this simplifies a lot. So, and what matters, okay, so let's go back, now that we have this idea, let's go back to our starting game, where we have a family of distributions. This is going to be our testing family. Have a family of distributions that are disjoint from, sort of disjoint from each other. Now, my testing challenge is going to be guessing which of the convex sets you gave me. And let's see what's the complexity. If the random variables are disjoint from each other, essentially, or mostly disjoint, once you get a couple samples, you will be able to tell me which which distribution you came from just by looking at where the samples are laying. So, but I'm only going to get 1 bit of information per sample that I get. So how many bits do I need to distinguish between these m possible random variables? Well, if I have a set of size m, I need at least log m elements in order to detect which element I'm coming from. So in the convex set case, as soon as I can find a disjoint family, for free, I know that the complexity, the query complexity, is going to be at least log m. Okay, let me give you some examples. Very easy example, 1 dimension. I have to consider sets that contain the origin. There's only one thing that I can do, which is consider dyadic intervals. The total variation has to be big enough, therefore they cannot have the same shape exactly. They have to be of different scales. The only thing that I can do to create different random variables is change the scale of the random variable. But I have random variables that have size that goes between k to the minus 1 until size k. In how many ways can I build dyadic intervals from size k to the minus 1 to size k? Well, log k. But log k then is the size of my family. So how many bits do I need? Logarithm of the size of the family, log k. This is exactly the log k that Chewi, Chen, and so on had found at the beginning. Now, let's consider for a second a slightly more complicated family. I'm going to cheat for a second, and I'm going to forget about the condition that I am centered. I'm going to consider general intervals. If I'm not considering centered intervals, I can instead, split k to the minus 1, and I have size k. I can fit k squared of them, but I'm taking a log k squared is roughly log k. So how much information do I need? Well, at the very least, log k. In this case, this is not sharp. This is not sharp, but it turns out that it's going to be sharp in the log concave case. Now, in dimension 2, the reason I wanted to consider this example is because it's some sort of one-dimensional shadow of the two-dimensional case. In the two-dimensional case, I can consider a lot of tubes going to the origin that have size k and thickness k to the minus 1. How many of them can I put in such a way that are non-overlapping? Roughly k of them. So in dimension 2, in the center case, even in the center case, I can have a k disjoint family, which means I can expect log k many options. These all turn out to be sharp in the log concave case. How do we improve from convex to log concave? Well, kind of brute force. So any convex set is an intersection of half spaces. And what I'm going to do is for each of these possible half spaces, I'm going to build a linear selector that basically is like some sort of value that's 0 and then very big. And that's going to select for my convex set. And if I do it in a smart way, it's going to give me some sort of nice potential. So I'm going to start with this sort of linear selector. It has a problem. This is clearly convex. It's the maximum of convex functions. It's not smooth, and it's not strongly convex. Well, making it strongly convex is very easy. I just start, like a convex part. Making it smooth is also easy. I just convolve it a little bit against something. And then I multiply it against something very big. The reason I want to multiply it against something very big is that then when I do e to the minus this, I get 1 where this is 0, and e to the minus a million outside. So I get a convex set. And this turns out to work. And I'm just going to do proof by picture that you can build these things and they're low information. So let's go to the equals to 1. I have these intervals. Now, what I'm going to do is, even for a very small interval, I'm going to take the maximum of a lot of possible selectors, which are going to be free. And I'm going to show it on the picture. So let's say that I want to construct the selector for this very bottom piece. I'm going to take the maximum of a lot of linear things with these slopes that are like smaller and smaller, sorry, higher and higher, of all of the possible dyadic intervals that contain my interval. What this is doing, if I had only selected the selector for my lower interval, I would be able to guess who it is just by, like following the straight line. But if I take the maximum with all of the selectors of the parents, you end up with basically two options. Either you measure inside, and if you measure inside, you don't really get a lot of idea about the actual size of the interval. It could be as big as you could. Or you measure outside, and if you measure outside, you also get almost no information about the size of the inner interval, because it could be as small as you could, because you don't know how many more of these little curves you're getting. And in practice, what happens with these potentials is that you learn is that they can take at most 3 different values, and in particular, they only learn 1 bit of information. Since you only learn 1 bit of information, the same argument from before applies. What happens in the uncentered case? In the uncentered case, we do exactly the same. The only difference is that now we consider potentials. You consider the dyadic intervals that eat your interval, that are contained in your interval. So you not only consider the centered ones, but you also consider all of the uncentered ones. And the same argument sort of applies. You can show that by taking bigger and bigger, that if you're outside, you're not going to learn anything. And if you're inside, you're already inside. So this argument applies all of the time. And on average, you can see that you learn at most 1 bit. How do we go to 2 dimensions? I'm going to do a super big sketch. You basically do, again, like I did here, a 1 homogeneous extension of this. And you can see on the picture, if this wants to work, I pick the profiles that I used before, and I 1 homogenize them to 2D. So now I get these potentials that contain the origin and are very big outside of this little ray, which is the ray that I built here. So the same idea works. Here you have to work a bit harder. This straight up doesn't work. You have to be a bit smarter. But in the end, things work the same. And it's essentially the same argument. Now, I also wanted to tell you a bit about what happens when kappa is very small, but I think I'm a bit out of time. Okay, so what happens if kappa is small and d is big? Well, as I told you before, in this case, you want to learn a Gaussian. If you want to learn a Gaussian, well, the law is very structured. It has the forma above. Every time you make a query to the gradient, what is the gradient? The potential, it's a quadratic thing. What is the gradient of a quadratic thing, a linear thing? So every time you make a query, you get a query to sigma to the -1. As I said before, if you query sigma to the -1, d times, you will learn the whole sigma to the -1 matrix, and you win. Now, the question is, can you learn sigma by querying sigma to the -1? The challenges, they're all associated to the covariance matrix. But what you have access to is the inverse. What is sort of the bottleneck? What's the problem here? When I query, let's imagine a matrix that has some big eigenvalues and some small ones. Here, the big eigenvalues dominate. Here, when I take the inverse, the small eigenvalues dominate. So I'm trying to learn the smallest eigenvalues of a matrix by doing queries to the matrix. This turns out to be a relatively hard task. But it turns out that there is a universal thing you can do. It turns out you could think about very smart algorithms, but it turns out that there's one really stupid algorithm that rules them all. If you think about it the following way, I start with a vector v1. When I apply it, I get some information. What information do I get? Well, now I know v1, and I know sigma v1. What am I going to do in the next step? Well, I'm going to be able to use v1, sigma v1, and maybe another vector. So I'm going to get some information that's going to be about this v2, sigma v1, and maybe if I build this vector out of v1, I'm going to get sigma squared v1, and so on. So all of the information that you could ever recover is about the vk's, k vectors and their vk's, and sigmas of these vk's. So instead of having to consider a potentially very smart algorithm, and the vk's, you don't know who they are. If you randomize, they may as well be a canonical basis. So every possible algorithm that you could ever design is going to be subsumed by a naive algorithm where you just pick k vectors, compute k powers of this vector and look at this. So this problem looks at a problem about building very smart algorithms, but it's actually a problem in approximation theory and a problem in like randomized linear algebra. This problem is very well understood. And then, you just pull from the literature and you get the standard bounds. So in conclusion, well, these are the like easiest useful probability measures, and most of their complexity is in the covariance. Yep. Is it all in the covariance? Well, that's a bit of a challenge. All of the examples we're knowing it is. We don't have a proof that there's no family with a non-trivial amount of information, but bounded covariance. So that's everything I wanted to say. Thank you very much.